I just got a new linter. I've been trying it on some of my clothes. It's honestly not doing everything I was hoping for. So I think it's time for me to learn to make my own linter. Come along and learn how to do it with me. Hi, I'm Jonathan Hall. And if you're not already familiar with linters for Go, not for your clothes, check out this video up here where I give you an introduction. But in this video, I'm going to be building a linter from scratch, following a tutorial. This is actually taken from a live stream I did a few weeks ago, and I've edited it and cut it down for size to be a little easier to follow and a little more interesting. I hope you'll enjoy it. If you're new here, of course, hit the subscribe button. And if you learned something today, be sure to hit like as well. Let me pull up the website for goanalysis lint. They have a nice section here in the documentation called New Linters. And then they tell how to write a linter. So I'm going to follow this tutorial they reference. All right, so the article says, we're going to write a useful linter for Go using the go/analysis package. Then we will integrate it into govet and golang lint. We might skip the govet part. I'm not exactly sure what that entails, but we'll see. I'm less interested in that. I'm more interested in the golang lint. What to lint? Let's find all printf-like functions that don't end in f. It's the Go convention to name such functions with f at the end. I don't really care about that linter, but that seems like a reasonable first project. So we'll just follow the tutorial, and then once we have the tutorial working, we can put in our own logic and lint something that we actually care about. Writing a simple linter. Sample program with an issue. Let's use the following example program for the explanation and testing. Here, my log should be my log f. Okay, so the function is called my log. See, maybe I'll copy that code into my editor so we can look at it more clearly. I'll make a sample directory for this project. I'll just call it my linter. Okay, so here's the code we're looking at. So it's pretty simple code, it looks like. Just a function called my log, but we want the linter to complain and call it my log f. So that's the code. That's the code that should fail the linter, and it should tell us that we need to put an f at the end of this. So that's what we're aiming for with this tutorial. What is AST? Usually such issues in code are detected by analyzing AST, or the abstract syntax tree. Let's visualize the AST of our program. By this online visualizer, it's marked out. What does that indicate? That looks like a really handy tool to keep in mind when we're doing linting, so let's keep reading. The most interesting part of the AST for us is the mylog function declaration. We simplify it to, so here we have an ast.funcdecl, function declaration. The name of the function is mylog, and it's some sort of ast.ident struct that has that information in it. But basically, this is a in-memory representation of the source code as parsed by Go. So this Go package, I'm not actually sure which package it is. It's called AST. I don't know if it's Go/AST. We'll get there, I'm sure. But this package is part of the standard library, and it is used when you compile Go programs. One of the first things it does, of course, is read your source code off of the disk and parse it into an AST. Unless there's syntax errors, then it stops. But assuming you have valid code, it reads it from disk into an AST like this. So this is part of the standard Go library. And that's one reason why there's so many linters for Go, is because there's just nice tools that make it really easy to do that, which we're hopefully learning about today. Let's continue. To analyze AST, we need to prepare it first. Okay. So I think this is the beginning of our actual linter. So that file I created here, I should probably put this, I'm going to put this in a subdirectory so we have it handy for testing, but it's not in the way for writing our linter. So now I have my main.go. I'm going to move that into a directory. I'll just call it example, I guess, for now. Now I should probably commit this somewhere. So I guess I'll make a project on GitLab. It should just take a moment, and then we can commit this and start pushing it up. All right, now I can commit those files, I think. Yeah, git add go.mod example. Just call it initial commit. Just push that up to GitLab just to see that it's there. Now if I refresh, we should see some code. Great. So now that it's live, and as I make progress today, I'll continue pushing it up there, and it should remain live. Okay, so where were we on this tutorial? We need to analyze the AST. We need to parse it first. So I think we need to copy this code into our main package. So let's do that. So we're going to create a file called main.go, and we're going to put this inside. Just pasted it. Let's save it. We have some sort of warning here. Oh, yeah, it thinks my log is unused, of course, because it's unused. I'm not using it yet. I don't care about that though. All right, what's next in the tutorial? We did our copy paste. Stack Overflow would be proud. Parser.parsefile parses source file and builds the AST. AST.walk visits nodes of the AST with our visitor. It continues visiting nodes until the visit method returns nil or all nodes are visited. In the simple implementation, we parse source files and visit all AST nodes. Okay, let's look at the code and see if all that makes sense. So parse file parses the source file and builds AST. It takes as arguments Go file names, and it ranges over those. And for each one, it passes the file path into parse file, which is part of the Go parser package. So that's not something we wrote. That's part of the standard library. And then if there's an error, it does a log fatal. And then, so assuming it succeeds, then F contains our AST. So then we walk our AST, the abstract syntax tree, and we use this visitor struct. Presumably it needs to match an interface. Yeah, it needs to match this visitor interface, which just takes a single, it's an interface with a single method of visit that takes one argument and one return value. And so we can see that's implemented here. So this visit receives one node at a time, and something else is responsible to pass all the things one at a time into that function. That's what we have here. So if node is nil, we return nil. Otherwise, it looks like we're just printing stuff out. But we should run this and see what happens. Let's do go build main. Go build. Yeah, seems to work. It just prints out a whole bunch of stuff. It prints the file itself first. Is that expected? Not sure why it does that. I guess that is what it's doing. So it prints the node first, and then it prints, and I guess the first node is the whole file. Maybe is what that means. And then for each sort of symbol or section, yeah, I can see it. So here for the func, it's like the whole function is one node, and then it prints the details about that. So that I see what it's doing, and it makes sense. All right, back to the tutorial. What's next? So yeah, we already jumped ahead and did this part that it's telling us to do next, where we ran it with the example.go. You can see that it visits and prints all nodes. Now let's write linting in visitor.visit. Okay, so we can put some sort of linting logic in there. So I guess I can just copy this. I hate copying and pasting code that I don't understand, but I don't understand it yet, and we'll come to understand it over time. So we'll just do it anyway. So let me save that to resolve imports. Okay, good. Actually, you know what? Before I do that, let me undo that. Completely undo that. Okay, I want to commit this. You know what else I'm going to do? I'm going to add a README that has a link to this tutorial for future readers. Whoops, wrong button. There we go. I'll make the README a little more explicit later, but for now, that's a good start. There we go. Got a nice little README there with a link to the tutorial. I'm going to close this tab. I don't really think I care about that the rest of the video today. All right, so I was going to make this change. Let me do that again. So I wanted it in a separate commit. That's why I did what I just did, just to have a nicer history. And also I can look at the diff that way and see what it actually changed. All right, okay. Let's paste that. Yeah. So we can see that when I do diff, bytes is removed for some reason. Go printer is removed and strings is added. And then here's the actual changes. So we're checking to see if it's a function declaration. And if it's not, then we just return the visitor as it is, this. What matters for now is that we're only interested in function declarations. So that means that constants and variables and packages and anything else, we're just returning without making any changes. So then we look for the parameter list from the function declaration. So we call, I'm assuming these are all nested structures or structs. So func_decl.type.params.list. If the length of the parameters is not 2, then we return. So because we're looking for printf-like functions, so that means that it takes a format string and a list of arguments. So that's what this comment here is explaining. So the first argument should be a format of type format string, which I assuming we're going to check the string type in a moment. But first it should be 2 arguments. The first one is the format string. The second one is the variadic argument of ... interface, or ... any if you're using Go 118 or later. So that's why it's looking for specifically 2 arguments. If you have 3 or 0 or whatever, then it's not it's not relevant to our linter. Let's keep going. Okay, now we're checking the type as I expected we might. So we check the first param type. It's doing a type assertion here that it's of type *ast.ident or pointer to ast.ident. I don't know when this would ever fail. Yeah, I don't know how you would. Maybe it can, but I don't know how the first argument to a function could not have an identity, not be of this type. I don't know how that's ever possible, but whatever. I guess it's defensive programming. And then we check if the type's name is of string. So good. If it's not a string, if it's an integer or a struct or a context, whatever, then we just return. Or early return, and we're not going to trigger the linter failure. Then we do something similar with the second parameter. Oh, so this answers my question. The first one could at least be a variadic. Well, I'm lying when I say that, but I said that I didn't know what other type it could be other than an ast.ident. Well, here's one example. It could be an ast.ellipsis. However, that would never be possible on the first parameter of a function with more than one parameter, because this is only ever valid as the last parameter. So I still don't know what else this might be, but I did learn just now that you can have at least ast.ident and ast.ellipsis as parameters. So that's interesting. So this does the same as before. If it's not an ast.ellipsis type, then it cannot be the variadic arguments that we're looking for. So we can return early. And then next we check to see if the type of those, I don't know what ELT stands for. Well, why don't I find out? Come over here, and with the magic of my IDE, I will find out what ELT is. Ellipsis element type. There we go. That's what it is. So if the second parameter's ellipsis element type is not an interface, then we early return. So by now we've confirmed that it is a variadic argument and that it's an interface, but we haven't yet confirmed that it's the empty interface. So that's what we check next. If element type dot methods is not nil and the length is not equal to 0, then it's not the empty interface. I don't know when methods would be not nil. Details I don't understand about this yet. This part makes perfect sense. If there's more than one argument, or more than one method in the interface, then it's not an empty interface. So now we are through the thing here, and we check to see if the function declaration's name.name, that's cool, ends with f. And if it does, then there's no problem. If it doesn't, then we print out an error. Print like formatting function %s should be named %sf. Okay, so we made it through the changes that we just made. Let's see what the tutorial says next. I'm guessing we're going to run it and ensure that it works. All right, let's do that. Go build main.go. Actually, I'm going to go build dot. That's safer. And then let's do linter tutorial with the input. There we go. We built a linter. That was easier than I thought. Printf-like formatting function mylog should be named mylog_f. Now, we still haven't built one that's compatible with Golang CI lint, but we built a linter, so we're partway there. I think that's the next section here. We have implemented a simple linter without goanalysis or any other frameworks. Let's move on to how we can use goanalysis to improve it. Yes. GoAnalysis is an API for modular analysis. Also, it's a common interface for all linters. This API simplifies developing a new linter. Well, not all linters. Not mine, not yet. Soon will be. This API simplifies developing a new linter. It forces using best practices for static analysis, for example, working with one package at a time. Okay, the primary type in the API is analysis.analyzer. The primary type in the API is analysis.analyzer. An analyzer statically describes an analysis function, its name, documentation, flags, relationship to other analyzers, and of course, its logic, of course. To define an analysis, a user declares a variable of type, pointer to analysis.analyzer, okay? So I guess that's just the definition of the type. Let's pull this up in the Go doc. If you're not familiar, this is the best tool in the world. You can look up the documentation for any Go package, as long as it's public, whether it's in the standard library or not. I guess it's not the standard library. It's apparently Xtools, but that's kind of unofficial experimental standard library is what that means. But that's cool. And we're looking for type. So I think that's the same that we just saw. Indentation's funky, but otherwise it's the same. All right. The most interesting field is run. It's where linting logic lives. Okay. It takes an analysis.pass as an argument. And there's that definition. A pass describes a single unit of work, the application of a particular analyzer to a particular package of Go code. The pass provides information to the analyzer's run function about the package being analyzed. A lot of this feels like it won't make sense until it makes sense, if you know what I mean. Like each sentence alone might make sense, but I'm not quite putting it all together yet. A pass describes a single unit of work, the application of a particular analyzer to a particular package of Go code. So you might have 25 analyzers, I'm guessing, since like goanalysis lint has all these different linters. I'm guessing each one of those counts as an analyzer. And then a pass is like a mapping between a Go package and one of those. So if you have, let's say your project has 5 packages and you're running 5 linters, then you have 25 passes, is how I understand this so far. The pass provides information to the analyzer's run function about the package being analyzed. It provides operation to the run function for reporting diagnostic and information back to the driver. Okay. The fset, files, pkg, and types info fields provide source positions, the syntax trees, type information for a single package of Go code. We don't need type information, so pkg and types info aren't needed. Wait, but do we need to know that the first argument of printf-like statement has type string? Yes, we need, but AST contains enough information about that, therefore we don't need type checking. Okay, so I guess for this particular exercise, we can ignore pkg and types info, but they're available if you need them, if you're doing a more advanced linter. Why do we need GoAnalysis? There are 2 main reasons to use GoAnalysis: unified interface and code reuse. Sounds like a useful thing to do. 2 useful things to do. GoAnalysis provides a unified interface for linters. It simplifies their integration into IDE, meta linters, like goanalysis lint, I suppose, code review tools, etc. For example, any GoAnalysis linter can be effectively run by GoVet. We will talk about integration later in this article. Okay, I'm probably not interested in that, but we'll read it, as I mentioned earlier. In our sample linter, we require a user to pass a list of all files to analyze. But the convenient way is to run linter without arguments or with /..., to run it recursively on all the files in all packages. We can implement it ourselves. I already did in the first version of goanalysis lint. Requires 100 to 500 lines of code. Or we can use GoAnalysis API to do this in 10 lines of code. I don't know. Do you think we should do the 10-line version or the 500-line version? Which would be make for more interesting watching? Oh, I'm going to do the 10-line version now. All right. Let's use GoAnalysis. Yes, let's. Let's port our simple linter to use GoAnalysis API. I've made the repository. This is funny that all these, not all, but many of these links have the strike through. I think that's a CSS mistake, but maybe it's intentional. I've made the repository Go printf func name for that. Okay. Do I care about this right now? So I think this is basically the same linter that we're building, but I don't want to just look at his repo. I want to do it myself, right? First, let's define the project structure by, or whatever, this pkg thing. That's outdated. The official Go project used something like that for a while, and they realized it was dumb, and they moved on. So I'm not going to do that. Otherwise, I'll probably follow this. I'll just put it in something called analyzer. So we're going to do something similar, but not exactly as the tutorial says. So I'll make a CMD folder, and I'm going to give it a name that matches my repo name, since that's what we're doing here. The linter tutorial. So I'm changing names to be consistent with my own thing, but it's the same concept. And then we're going to put this code into a main package there. So effectively that main I already created is going to be obsolete, I guess. I'll probably delete that when I get there. All right, so these imports are not working because I haven't added them yet, but I want to change this. This is not the import path I want. I want to use, this is supposed to reference the current project I'm building, right? So I'm going to use my own name here, gitlab.com/boldlygo/ what did I call it? Linter tutorial/analyzer. Now that package doesn't actually exist yet, but that's what I'm going to call it. And this other one just needs to be imported, which I'll worry about in just a second. I'm going to create this analyzer file first. So let's copy and paste this dealio. All right, now this one fails, but if I do go mod tidy, it should fetch the things I need. Or I could do go get in the package name. This is just a shortcut because I don't have to remember the package name that way. Now you'll see it's working, and this one is also working. So I've created that package myself. That's this file here, and then I imported both this one and this one by running go mod tidy. You know what I think I forgot to do though before I mess with that? I want to commit the changes I already made to main.go, the original one, right? Yeah. So all this stuff that we just walked through, I want to commit that. So I'm going to do that now. All right. So that's the previous step. I should have done that earlier. So now I want to add CMD and analyzer. All right, so the two packages that are referenced here are both in the xtools module. See that? So the one is the goanalysis. That's the one we've been just looking at. And this other one, don't know what it is yet, but I'm sure we'll find out. It's under goanalysis single checker. So those are both imported with this, and then we have two indirect dependencies. All right. So we've done that, but I don't know what has happened yet. It says notice what's changed. I think I'm going to go just like I did with the others. I'm going to let's just walk through this code and see what it does, make sense of it. So main is pretty straightforward. It has a single function called main, of course, which calls the single checker main. I guess it's a good time as any to learn what that single checker thing does. Package single checker defines the main function for an analysis driver with only a single analysis. Okay. Simple enough. So that's if you're running this in Golang CLint, for example, you wouldn't use this because you have multiple analyses. But since this is a simple test, it's just like a simple bootstrap for a single analysis. That's nice. And then we call analyzer, which is this thing we just copied and pasted with the other file. Let's see if we can make sense of that. So here we name the linter, I guess, or the analyzer to be more technically correct, and it's called go printf func name. I'll leave it alone. I don't care. And it's something to describe what it does. Checks that printf-like functions are named with f at the end. All right. And then we have a function called run. And then we define that the run function is this run function. So this is the actual logic that's happening. It takes a analysis.pass as we read in the tutorial documentation, and returns an empty interface and an error. So we're assigning to this variable called inspect a function. That function takes a node and returns Boolean. All right. So this is similar to what we had before, right? Yeah, in fact, it's very similar to what we had before. So if our node is not a func decal, then we return true. We early return. But previously in the other version over here, we were returning v. So whatever that single checker does gives us an interface that's a little bit more intuitive to me. So we can apparently return a Boolean. True probably means keep traversing the tree, and false would mean stop traversing the tree. I'm expecting. I'll check in a moment, but I expect that's what that means. So that's a little more intuitive to me than this earlier version where we're returning the AST.visitor. So, but it looks like it just does a simple conversion along with probably other things in the background that make this a little more intuitive. But logically, it's doing the same thing. So here you recall we're calling funcDecl, and if it was not okay, we returned early. Exactly the same here, except now it's returning a Boolean instead of that visitor type. Then we do the other checks as well. Do we have 2 arguments? If not, if it's not 2, then we return early. Is the first one an AST ident? If not, return early. Is the first one a string? If not, return early, and so on and so forth. So it's exactly the same as before, just modified to return a different type. And then now this is the interesting part. So if you'll recall before, when we had a failure, we just did an fmt.printf. We just spit it out to standard output. Now we call pass.reportf. We give it the node position, which is probably, I'm guessing this has to do with a line number and file, probably a file name, line number, and maybe the position on the line is probably all that information. And then it tells us printf like formatting function %s should be named %sf. So it's the same verbiage essentially, but it's done in a different way. So it's, rather than printing it directly, it's passed up the call chain. It's passed back to the single checker. And then here, okay, so now, so that's inspect, but we've received this pass argument, and we use that pass argument to go over all the files. So remember, a pass represents a package, so it could have anywhere from 1 to n number of files in that package. And so here we run over each of those files, and we call ast.inspect on that. So that's pretty straightforward. And then we return nil. So I don't know what that means. I don't know what, if we wanted to return something, what it would be. I don't know why that's nil. Maybe if you're modifying it in some way. I don't know if you can modify the source code as you're doing this, but this linter isn't doing that. So I guess we're okay. So we've made it through that. Let's go back to this tutorial and see what's next. Notice what changed. We used ast.inspect instead of ast.walk. Yep, it requires less code. To do that, we just need to remove the visitor and return true instead of the visitor. Yeah, I noticed that, and I actually like that a lot better. We iterate over pass.files to get syntax trees, ASTs for the current package. We don't load them manually. So I guess that's a detail I didn't call out. It wasn't obvious, but these files aren't like disk files or whatever. These are the ASTs for the files, apparently. Yeah, it's a slice of pointer to ast.file. So that makes sense. And then finally, we report about found issues with pass.report instead of fmt.print, as I pointed out. So great. Let's run this and see what happens. Go build.cmd. There we go. So we have the failure, and it. I was guessing that it would include the file name. You remember I was guessing that this node.pos included a file name, a line number, and possibly a line, like a column or a position on the line. It looks like it has all of those. So it's line 5 and position 1. Is that accurate? Here it is. Yeah, nope, that's the wrong file. Line 5, yes, and position 1. So the function declaration starts on the first character. So yeah, that makes sense. So and this is the information that your IDE, like VS Code or Golang or whatever, will use to put the squigglies under the right part of your code. It can read this data to know that. All right, what's next? Oh, so here they ran it without an argument. So let's try that. And we get a nice little help output. And then this help output comes from the single check function, right? Yeah, single checker.main. I guess it reads command line arguments and everything for us. And if they're not present, then it gives us this nice little output. So that's cool. Thanks to goanalysis, I get a lot of command line options. Now it's time to test it again with example source code, which we've already done. And we get the same output, the only difference being the different file paths since we're using different file names. Yes, it works. Great. ast.inspect versus inspector. All right. Did you notice an ineffectiveness in ast.inspect and ast.walk? We visit every AST node, binary expressions, variables, constants, etc. But we need only function declarations. Can we visit only them to improve performance? Yes, we can. goanalysis contains inspect.analyzer. This analyzer filters AST nodes by types. First, we should require it as a dependency. Okay, I'm happy to do that, but it doesn't tell me how. Change the run function too. Okay. All right, perfect. So let's just copy this. I want to look at the diff and see what happens. We're replacing run with the new run version. Let's see what the difference is. All right, it fortunately was able to detect the correct inspect. Actually, I don't think that is the correct one. I don't think this AWS Go service director thing is the right one. I think it's, I don't think that's right at all. Let's see if we can find the right one. Oh, I don't know where it is. Okay, so what I'm going to do is I'm going to, because the tutorial doesn't actually tell me where it is. Oh, it does tell me to require this thing. I missed that part. So let me copy this line. There we go. I don't think that's going to get the right one, but let me delete that and see if the resolver can get it now. It's still wrong. So I don't know what the path is, but I think I can find it by looking at that repo we saw before. There's the path we need. There's the input path. So let's replace this silly AWS thing with that one. There we go. That's the right one. It's all part of the xtools thing, so it all resolves out already. Perfect. So let's look at that diff now. All right, 2 new imports as expected. One line change here, but the indentation changed on the other, so they've changed color. And then let's see about the actual logic here. Pass result of inspector.analyzer will be set if we've added inspect.analyzer to requires. Okay. Filter needs nodes, visit only them. Okay. And then we say ast.funcDecl. We're passing it. So this syntax here essentially sets it's a way to create a nil pointer to something of this type. So presumably whatever uses node filter just looks at the types of the arguments. And so let me just pull up my editor here and I can show you. So that's the original. You could do this, I'm guessing. You could do that, and it might look a little bit more natural, but it uses memory because it allocates a pointer to this type, and it allocates an actual instance of that that struct. But by doing it this way, even though it looks weird, it uses less memory. So it's a slight memory optimization is what that is. Then we call inspector.preorder node. So we pass our node filter, and then function node ast.node. So rather than using that inline inspect function, we're now passing that function to inspector.preorder, and this one doesn't take it doesn't return a boolean, so that return true is always returned changed to just return. It returns nothing. So here's the old function signature. Func node ast.node return bool, and the new one is this, just func ast node with no return value. I hope that makes sense to everybody. I don't know why it doesn't take a boolean, but it doesn't apparently. Okay, so and then rather than ranging over these pass.files, we just call this inspector.preorder, which does the ranging for us. So it looks pretty straightforward. It's a little bit nicer, I guess. All right, let's run this one, see how things go. Behavior looks the same. Let's make a commit. What did we add here? We added something called inspector. Sure. Whoops. Can't spell very well. All right. Let's just push this up to GitLab 2. What's next? Well, we've changed the AST walking a little bit. Now we use inspector.preorder and don't return anything from the visiting function. The excerpt from the inspector's comments explains the profit from its usage. So I'm going to pull this up on, we just had that open, but I'm going to pull it up on here so it's easier to read. All right, so it's quoting this part right here. During construction, the inspector does a complete traversal and builds a list of push pop events and their node type. Subsequent method calls that request a traversal scan, what? Subsequent method calls that request a traversal scan this list rather than walk the AST and perform type filtering using efficient bit sets. I love efficient bit sets, don't you? Experiments suggest that inspector's traversals are about 2.5 times faster than ast.inspect, but it may take around 5 traversals for this benefit to amortize the inspector's construction cost. If efficiency is the primary concern, do not use the inspector for one-off traversals. So in other words, this is probably actually making things slower for us, up to 5 times slower apparently, since this is a single invocation of a single analyzer. But if you're using something like golang ci lint, where you're running 15 linters all at once, then you get the benefit. So I guess that's what that means. Let's continue. We expect our linter to be used from linters run like golang ci lint. Such linters contain dozens of analysis analyzers. Therefore, we are sure that the inspector construction time will be amortized. And even if it's slower, it's just a simpler API to traverse syntax trees. I think that makes sense, yeah. Testing. All right, it's time to test our linter. I would love to do, I like to do TDD. So the fact that we're doing testing after sort of is backwards there, but that's okay because I'm just learning how this works right now, right? Once I finish this testing part, then I'll understand how it works, and then I can use TDD to build a real linter, which I'll probably do. In the file pkg analyzer test, which we're going to rename to just analyzer test, we write this. So let's do that. It's not the whole thing though. I mean, I know how to finish it, but it's not a full file. There we go. Well, it wants it to be a separate thing, so I'm going to do this. It expects it to be a separate package since it referenced the analyzer package directly. So I'll do that. I'm going to move this import to another group. I like to keep 3 import groups. If you're wondering why I did that, the first one is for the standard library. The last one is for imports in the same Go repository or same module, and then the middle one is for anything else. Oh, the test failed. So sad. Oh, we don't have test data installed. Okay, well, we'll get there, I'm sure. Actually, before we do that, let's see what this test is trying to do. It's trying to get the current working directory, okay. And then it tries to read file from test data. Okay, that makes sense. And now I know why it was failing. If you're not familiar, the Go tooling treats test data as a special directory name, and it's intended for containing data that's only used in tests. So you can put even .go files in there, and they won't be compiled and linted and everything normally, which is great, especially for something like this, where we probably want to put, if you're building a linter, you want to put a whole bunch of Go files in there, and some of them might have broken code in them that if you didn't put them in test data, it would probably break your CI pipeline, because your CI pipeline would detect that there's broken Go code in your repository and tell you syntax errors or lint failures or whatever. So that's what test data is for, and that's why it's being used here. So now we need to put some files in there. Now it wants us to do test data /src/p/p.go. It seems kind of verbose, but I'll do it anyway for now. Maybe there's a reason. Now it wants it in. This is a little bit unusual. I don't like this. They have a single test data directory at the top level of their package. I'm going to go ahead and do that right now, since I don't know where they're going with this, but I usually put my test data right next to my test. So in this case, it would go in the analyzer directory. So I'm not crazy about this, but until I understand fully what they're doing, I'm going to go ahead and follow the tutorial. Right, test data /src/p. And I'm going to create this file that contains this stuff. And it contains a whole bunch of functions. And my linter doesn't like it. My linter is running on this project with default settings, and it's complaining that I have code that's not being used. So I probably should disable that linter for this package. Yeah, I suppose I'll do that right now. I'll do it at the top here. That should make the linter happy. That little directive just tells the linter don't complain for the linter called unused. And this is the reason why, because they're for tests. All right, back to the tutorial. What's next? Now, all right, let's run the tests and see what happens. No such file or directory. But So I think it's because I'm not in the same directory structure they suggested. Yeah, they call filepath.dir twice because they have to traverse up the tree twice because they had the PKG path in there, which I don't have. So I'm going to remove that. I think that'll solve it. Yeah, now it passes. All right, let's continue down this tutorial. We're getting close to the end here. Did we finish with tests? No. Let's check our code coverage. Okay, let's do that. Let's add the dash cover. We covered 83.3% of statements. I know what he's doing here. So what he's looking at, he's configuring VS Code to show which code is covered and which isn't, which I'm pretty sure happens by default. Yeah. So you can see here that this statement is not covered by my tests. It's got this red background. This one is not covered by tests, and this one, and this one. So we can add some more test coverage if we want to. There's a screenshot. It's a little bit hard to see. Screenshot from VS Code. Oh my gosh, he doesn't use dark mode? What's wrong with this guy? You all use dark mode, right? Okay. Anyway. So yeah, some of these are not covered. So I'm not actually going to follow his tutorial here because I'm going to just do this myself. But we can see here that this is the first one that's not covered. What is it doing? It's the first param type isn't an identifier. Okay, I might actually have to look at his his example to figure out how to do that because that's what I was saying before. I don't know what else it could possibly be. So I'm going to go back on my word just immediately and figure out what the heck I can do to trip that one up. Some code blocks are collapsed. Yeah, okay. I've checked again. All cases except one are uncovered. The uncovered one is. I don't know. He has only one. Oh, he added this, I guess. All right. I'll go ahead and add. He adds 3 to cover the other 2. Okay. So I'll add those 3. That's here. Second arg is on ellipse. Okay. Printf like, but with extra interface methods. Okay, so here it's an interface that takes that has methods instead of an empty interface. We talked about that earlier on. All right, and then what's this other one? Okay, so he agrees with me. He can't find a test case for this one. So this apparently cannot happen. Let's look at our covered code again. So now this is the only one that's not covered, and this is the one that actually cannot happen, apparently. So my early guess was apparently right. Still, it's not bad practice to check for that. Maybe some future version of Go will support a different type of argument or something, and you want to check for that. Or more likely, it's just you want to be clear that you're covering your bases. So somebody, if you leave that out, if you did this, somebody else reading your code might go, "Wait, you forgot to check errors or whatever." So principle of least surprise, I think, makes it useful to still put that in there, even though if we expect it will never possibly trigger. All right, did we finish with tests? No, we've forgotten about important tests. About this person forgot some articles in his English. He's probably not a native speaker. No, we've forgotten about an important test case. I'm not sure, but let's copy this and see if it makes sense. So the important test cases we have functions that look like printf, but they take an extra argument. So in this case, it's called extra arg. Extra arg. What's the difference here? Oh, this one it's a string, and this one is an integer. So apparently he wants to cover these, which probably makes sense. But our current code does not. Yeah, so we run a test here, and we get failures. So let's fix our code. So now we're doing some TDD. We write a failing test first, then we make the code work. I like that. So here we are over Analyzer. I'm not sure exactly what, I can guess where he wants us to go, but params. So now he changes it to if len params is less than 2 rather than exactly equal to 2. So let's do that. And then next, if, okay, so then basically he's requiring that only the last 2 arguments are string and variadic any. Anything before the last 2 arguments can apparently be anything. So here, rather than checking params 0, he checks params len params minus 2. Makes sense. This stays the same because we're still calling it format param, although he renamed this from first to format, which makes sense. Since it's no longer necessarily the first, it could be anywhere in the string list. All right. And then he changes this one to args. So we're going to do args param type. And then args param is, rather than 1, it is len param, len params minus 1. I think we're done there. Let's see if the tests work now. Yay, the tests pass. TDD for the win. Let's commit our changes. Should have committed go.sum a long time ago. Anyway, I'll do it now. All right. Run it on Go source code. Haha, let's do it. So go install.cmd. All right, Linter tutorial is now installed in my path. And then we're going to cd to go root src. This isn't useful because I don't have go root configured, but it should be user local go. There, that's what it really wants. All right, we're going to run the linter tutorial on the entire Go standard library. I bet it'll fail somewhere. The log package at least has some functions that I think will fail, but we'll see. I don't know how long this is going to take. There we go. One failure. Format function warning should be warning F. It's an internal function, so it's not actually even in something that it's not an exposed function in the center library. Curious what it is. Let's look at it just for the heck of it. Internal coverage pods. I don't know what that is. Pod encapsulates a set of files emitted during executions of a coverage instrumented binary. So this has to do with actually code coverage statistics, apparently. It's very definitely an printf style function. It takes a formatting string and a list of arguments and prints them to standard error. Yeah, okay. So it wasn't even a false positive. That's cool. Still don't think it's very valuable, but it worked. All right. So when he ran it, he got back 30 issues. So apparently they fixed some of them. Some of them are valid. Some of them are false positives. That's interesting. I don't know why it's not showing up in my test, but it's a false positive because this is not a formatting string. It's a query string, right? With the arguments fill the placeholder values. That would be like select star from foo where user ID equals $1 or something like that if we're using MySQL. That's what this is supposed to be for, I think. I'm not sure why I'm not finding it. The proper fix is to trace all calls inside such functions and find out whether a format argument go to formatting functions like fmt.sprintf. Maybe we will do this in the next post. For now, let's make a simple fix and require that format argument name is equal to format and don't allow return values. We will increase precision of our analysis, but will decrease recall. Statistical stuff. So I don't 100% agree with the idea that that's the correct solution, because I mean, that would not have caught the one that we actually caught, right? This one. I don't think it would have. Let's check. It would have actually caught this one because we're calling fmt.fprintf, but it wouldn't have had to. Like, there's no reason that we would have to be calling fmt.fprintf here. You could implement that yourself, right? Or maybe you're calling a log.fprintf or infof or something like that. So I'm not sure that is the correct solution for this. Not that it really matters since I don't really want this linter to work, but it's a way. I mean, certainly it would be a positive way to verify that it is a formatting string, but it could have false negatives, I guess is the point. So I still am very curious why I'm not catching these false positives. He got 30 failures, I got 1. I don't even know where to start debugging that, or I would do it. All right, let's see if we want to finish up here. This is the part I might want to skip. Integrate with govet. Oh, it's really easy. It's a command. It's not even integrating from a source code level. It's integrating the command line tool level. So you do govet and then vet tool, and you tell it which tool. And so that would be the path to my binary. So yeah, I'm going to skip that. I don't want to bother with that. Oh, here we go. How to integrate with Golang CI lint. This is much more interesting to me. Golang CI lint is a linters runner. He's the author of it. It contains dozens of linters. Let's add our own. The main part of adding it is, I don't know if this is in our project or in Golang CI lint project. In the end, don't forget to do make vendor. So this has to be on the Golang CI lint project. Let's pull that up. I'm not going to create a pull request, but I want to see how it's done. So he's saying to close that. Linter. So linters. And then go print. So we add our own linter here. So his example is go print f func name. And that exists here. I'm pretty sure he added this just as an example, although you can use it. It is an actual linter. So here's the file, and then he has the new go print f func name there. And then make a pull request. So, oh, he put all the source code, the whole thing in there. But I suppose it could be a link to an external library that you create. So, you know, if I were to create a linter that I wanted to add here, I'd probably create my own library, and then have the pull request just reference it. So here we can see his pull request to add that. I guess he kind of did the same thing, maybe. I don't know why he didn't mention that in the tutorial. He left that out, and maybe there was a reason. But here there's some, I don't know what that is. So here's the thing he mentioned. It looks like we're adding configuration hooks of some sort. And that seems to have been left out in the tutorial. But it's also really simple. And then they're using vendors directory, which is why he mentions that here, make vendor readme. Okay. If I ever commit, or if I ever submit a pull request to Golang CI lint, I'll be sure to do that. But that's what that's for. That's kind of cool. So I think we're basically done. We've built a linter. I think this is a good stopping point. We've built a linter. We've tested it. We've talked about some different bits. I think I'll be doing this again next week at the same time. So I hope you come back. I hope to see you all here again next week. Thank you so much. Talk to you later.